back to the closures. Thank you. So as part of an effort to highlight some of our own researchers and as well as to better integrate postdocs into our broader community, I invited Jack O'Brien to give a talk during our series. And I also wanted to give him an opportunity to talk about himself and his research. So go ahead and.
All right. So hi, I'm Jack. Many of you know me. I've been a postdoc here for about 2.5 years now. I graduated from Michigan State University. I did my thesis on neural network emulators for type 1A supernova and trying to determine their progenitor scenarios. And now I work here, mostly working on this model SELDON that I'm going to talk a little bit about, which is a much more data-driven approach for also modeling supernova and other kinds of transients.
Yeah. All right, take it away.
So again, SELDON is Supernova Explosions Learned by Deep ODE Networks, and I will explain what all of that means throughout this talk. And this is a joint effort between some people here at UIUC and some people at Northwestern, and we're all under the SKY Institute, which is an institute for AI applications to astronomical data. Let's see if my laptop works. All right, so to start off, I'm just going to talk a little bit about what transients are and what I mean by them. So this, to me, is kind of a transient. You know, it's nothing, and then it's there, and then it's gone. There's a lot of different things that can be referred to as transients, but the idea of them is that they are transient phenomenon. They don't stay around. They're not like variable stars. We can keep looking at them, or AGN, where we can observe them for years and years at a time. These things appear and then they tend to disappear. Most of these tend to be extremely energetic events, and there's many things that can be included into the category of transients, from tidal disruption events, kilonova, supernova, all kinds of cool stellar explosions that I really like. One thing I really like about transients, especially, is that these are things that connect all areas of physics. One of the reasons I like studying transients so much is because I get to do physics at all different scales. I work a little bit in rate of transfer, and part of that is just doing even going down to atomic modeling and trying to figure out what individual energy levels are for elements that we don't have, all the way up to extragalactic scales, which I'll also discuss. So especially close to my heart for transients are supernova. Here's a beautiful picture of a nice supernova, SN 2011FE. It's a fairly famous 1A that was very well sampled and very close by. And these guys are pretty broad. There's a lot of different kinds of supernova, or things that we call supernova. They can be the explosions of massive stars or the explosions of stellar remnants. And these things are massively energetic. These things can outshine the entire brightness of their host galaxies, and they release more energy in just a couple of weeks than the sun will release over its entire 5 billion year lifespan. And these are especially interesting to astronomers for a variety of reasons, but they also have implications for things like star formation in galaxies, and even being sources of different kind of multimodal astronomical signals that we get, so neutrinos or gravitational waves and things like that. And then, of course, we classify supernova generally by their spectra. Again, a thing I like about transients is their connection to things that are small as well as what's big. The spectra are usually determined by the actual individual composition of the supernova itself. And we usually classify these things purely observationally based on the spectra. Different types of supernova are really classified based on the lines that we see, not necessarily anything that have to do with what kind of events led to their explosions in the first place. Mostly for historical reasons, though we do have a better idea nowadays of what causes them. So one of the reasons that we care about these guys so much, of course, you've probably heard in a million talks, is cosmology. These guys are famously standardizable candles. Here, a picture of a few different type 1A supernova that, with the scaling and stretch factor, you can align them all to a similar grid for their brightness versus time, and use this to discover the expansion rate of the universe, which of course led to the famous Nobel Prize-winning discovery of dark energy in 1999. Though these values are still in tension with the CMB. And then there's other class of supernova that we also use as cosmic distance estimators. One in particular is type 2P supernova using the expanding photosphere method. If you treat a big ball of hydrogen exploding in the sky, you can basically use Stefan-Boltzmann law to figure out how big it is based on how bright it looks. And from that, you know how far away it is. And of course, nucleosynthesis, the stuff that we're made of in the universe, these mostly come, or at least the heavier elements come from these kinds of transient phenomenon. Especially of question is, where do these elements come from and in what quantities? You may have seen many charts like this. If you look closely, no two charts like this show the same ratios or the same sources for the element. Still an active area of research and connects deeply to nuclear and even subatomic physics. And lastly, one thing that I care about in regard to transients is the explosion physics itself. This is a simulation by Rutger Packmar at Max Planck Institute of a double detonation scenario for type 1a supernova, which is currently still not clear what progenitor scenarios cause them to explode. And there's other aspects of all kinds of supernova that we don't know and are still actively being studied, such as their flame propagation, ignition mechanisms, or even what kinds of objects are exploding in the first place. And all of these different questions and areas of study require good data and lots of data that we don't always have, but we will. So observing these transients in the past wasn't as much so a big data challenge. We had a few, maybe like tens of thousands of spectra and maybe an order of magnitude more light curves for supernova. But in the age of Rubin, things are going to change. The Vera C Rubin Observatory, as many of you know, has recently just come online, and it also kind of represents one of the largest scale challenges astronomy has ever faced. This is one of the largest cameras that we've ever had on a telescope, and especially important is Rubin is going to provide up to 10 million alerts per night of transient phenomenon in the sky that need to be cataloged, processed, classified, and all of those things. Especially in regards to supernova, there's going to be a massive volume in the discovery of new supernova. This is a plot from Alex Gagliano, though a little outdated with Rubin's start date. But we're going to have an order of magnitude, at least more supernova discoveries, which sounds great for science in all capacities, except that Rubin is still a survey telescope. We're not going to get, very, very dense photometric time series for these transients, and we're also not going to get spectroscopic observations. We're not going to have as much, we're going to have a very large amount of data and a large amount of light curves, but maybe not in as much detail as we need to do all the science that we want to do. So in order to do this, we're going to need some process that can model or identify or classify or predict supernova so that we can target them for specialized photometric or spectroscopic follow-up with dedicated surveys based on the kinds of science we want to do and figure out when is the best time to take that kinds of data. So I'm going to take an aside a little bit and discuss modeling time series in general, because this is getting a little more into the AI side, so I'm not as sure how familiar everyone is with this. So for time series modeling in general, I have a little cartoon of a time series, got my observations, and I've got some different channels that have some different kinds of data in here. So, all of these are happening at one time, and these are the kinds of inputs that you have to your thing. So most off-the-shelf traditional time series models are working with some kind of data like that has these nice properties, and they're allowed to make certain kinds of assumptions. So for example, dense sampling, usually you have all your channels all at the same time. And this is pretty common in image modeling, usually, right? If you're modeling a picture, you have your RGB channels of your images across the thing. You're not only getting like 2 red pixels and trying to figure out what the whole image is. Additionally, uniform sampling, and this is a relatively important part. A lot of time series data that you see modeled like modern AI is doing things that are on nicely spaced uniform grids, either sampled for real world processes by machinery that has like regular intervals, or of course in the popular case in language models, if I say 2 words in a sentence, I'm not worried that those 2 words are 4.5 words apart from each other. But more flexible techniques that can deal with kind of these gaps in data, they do exist, but they're generally not acceptable for the time scaling that's required to process 10 million alerts from Rubin a night. There's things like ARMA and carbon modeling, which are autoregressive models. And of course, as many know, you can take physical templates or simulation codes and try to fit your supernova yourself. But if it takes you 10 minutes to 2 weeks to fit a transient, you're not going to be able to handle 10 million alerts a night. So the problem that we have with astronomical time series is that it looks a lot more like this. So this is just an example of a simulated light curve with Rubin cadence from an elastic data set, which I'll talk a little bit about later. And using the previous example, it's kind of like having your data look like this instead, where we have completely random gaps in time. We have huge differences in error and lots of different kinds of uncertainty. And there's also no one type of uncertainty. These are heteroscedastic. They're not all the same distribution. Probably should put these through. Another big aspect of this is the data imbalance that we have to deal with. So if you look carefully at this light curve, I have some points in the U band here. I've got like 3 of them versus, my R band, I have much more dense sampling that even if I only had this data, I could probably infer some information about the supernova. So we have a severe imbalance in the types of data that we have, like the individual channels. And we also have the problem that in nature, some transients are just, yes.
Sorry, I'm very ignorant, not observer, but why would there be big gaps in the R in time spacing?
What do you mean?
Like, why would the R band disappear and then
Be either it didn't sweep that part of the sky because this was observed as part of some other like observing procedure, or there were clouds, or there can be a variety of phenomenon. LSST scheduling is complex and booked up for different people's science objectives, which isn't just finding all the transients in the sky.
But it could find the other band, but not the R band.
Well, you can only observe one band at a time because you have to change out the color filters.
Gotcha. Thank you.
Which is also another problem. We actually never have 2 channels at once. Yes.
Yeah, and is this actually a reasonably good case? Like, this is pretty bright.
Oh yeah, this is like one of the
time.
best observations in our training data. Our training data, this typical number of data points that we have is around 12
Yeah.
across all bands.
Right.
So yeah, it's very, very difficult to work with and model and a lot of uncertainties. Any other questions? So in order to handle all this, we need first something that can interpolate and extrapolate between all of the missing data, which, if you have a physical model or light curve templates or something, that's great. You just put your light curve template on there and you do a chi-squared best fit. But what if I don't know what kind of light curve template to use? What if I don't know what kind of light curve it is in the first place? And what if I don't want to run some sort of MCMC sampling? Additionally, we need to be able to handle these arbitrarily large time lags. There are decorrelation timescales, right? Some data points become less associated with other data points the further apart they are in time, and we can't make as many inferences. If we only had these points over here, and then the next observations were all over here, we're not really going to be able to say all that much about what's in here unless we have some kind of way of interpolating between these things. And then additionally, because we were trying to make a foundation model, we need something that provides a general enough framework that we can apply whatever we get out of this to other downstream tasks in addition to just interpolation. We want to be able to do things like classification or understanding physical parameters of the system. So again, we need some model that can do these kind of interpolations between all of our missing data and maybe even use some data from single channels that we have to make some inferences about what's going on in between. So our solution is our model SELDON. So again, as I said, this is a joint effort between people here at UIUC and at Northwestern, all through the Sky Institute. And these are some of our collaborators, as you probably are familiar with a few of them. And we've been working a long time to try to make a model that can do all of this. So as a quick general overview, this is the architecture of SELDON. Don't worry, I'll go through all of the individual components one at a time. But fundamentally, SELDON is an autoencoder. The idea is that it has an encoder, which is all the stuff on the left side here, and it tries to form some sort of vector representation of our light curves. And then it also has a decoder, which tries to do things like interpolate or forecast and things like that. And we call SELDON a time series foundation model for transients because these latent embeddings aren't just intended to be used for reconstruction, but also other kinds of tasks. Again, we want to find out not just, I can write a linear interpolator with good enough data, but I want to actually be able to predict what's going to do past the light curve points that I have, and also make some inferences like what class of transient it might be a part of. So what I mean by foundation models generally, so the idea of these things is that some model that you train once on a large corpus of data, which eventually Rubin will be able to provide us, though I think it's going to be a couple of years before Rubin actually provides enough data to fully train SELDON on pure observational data. And then we want to be able to adapt it to downstream tasks. So again, we have our latent embeddings, and we want to do all kinds of things like classification, interpolation, and prediction. And we're trying to make a general foundation model for astronomical time series. And currently it's mostly focused on transients, though extensions to other types of astrophysical phenomenon are totally reasonable in the future. But SELDON here is just the first step in building one of these kind of foundation models. Yes.
I mean, I assume SELDON because foundation, right? But how does a foundation model differ from other types of AI?
So the idea is that it's supposed to be able to handle more than just the tasks that's trained on. So for example, if I can do light curve forecasting and generate good approximations for the light curves, that means I probably have all the information in there that I need to do classification as well, because a different class of light curve is going to predict a different forecasted light curve. Or things like if we want to infer the redshift, right? There's a dependency between the magnitudes of the different photometric filter bands that we get, or observations each filter band that we get depending on the redshift because of things like K corrections and stuff like that.
Okay. So is this any different from machine learning plus ancillary calculations that use the output of the machine?
The idea is to not have to do those extra calculations, or at least if you do, it's just more AI. So going into the individual components now. So first I'll discuss how SELDON actually works to encode all of the information. So the encoder itself is kind of the core of SELDON. It is the thing that takes these irregularly sampled, noisy, heteroscedastic time series and tries to encode them to a single latent representation. And ideally like a small dimensional latent representation. We want to compress as much information as we can to a small space. This is also useful for other tasks, for example, data storage, and also making sure that we're not storing extraneous information in this space. So the way that this works is in a few steps. First, as I mentioned before, actually, I don't know if I mentioned it yet, we have a GRU ODE encoder. And the way that this works is we have some sort of hidden state here represented by I. And you can almost think of this as kind of like a scratch pad for the neural network that's on the side that it can write information to. And it gets updated every time it sees an observation. So the value of the hidden state at any one time contains all the information that SELDON thinks it needs to understand the evolution of the light curve up until that point. The hidden state gets updated. It's called a gated recurrent unit. This is essentially a few layer neural network that does some balancing between how much new information to add to the hidden state and how much information to ignore. And this happens with every single new observation. And then the interesting part that makes this different from a regular GRU network is that time lags are handled by evolving the hidden state with an ordinary differential equation. And the ordinary differential equation is a neural network. So this differential equation is parameterized so that we have a neural network that is equal to the derivative of h with respect to time. So anytime we have a lag, we get our new value of h, and we can evolve this differential equation to the next h that needs to have the value that it needs in order to provide the correct updates given the new information that we're going to get in our system. This is a little bit more boring schematic of the way this works. Our input embedding would be things like our fluxes, which filter came in, and some things like metadata, and then our time embedding. And we only give it, which is just a linear projection, so it's literally just the time scaled. We take only DTs, and we only take flux information. So this neural ODE here is an autonomous network. It only operates on the current value of the hidden state. It does not take a time component. Again, when we don't have data, we evolve the neural ODE forward to update the hidden state. And when we do have data, we take information from flux observations from the GRU cell and use that to update the hidden state until we get a final hidden state. Next, SELDON resamples the hidden state onto a uniform grid to make it easier for more traditional sequence models to encode the information. Because again, as I mentioned before, a lot of these kind of sequence encoders always rely on some assumption that the data is equally spaced and equally dense. So it does that. After it finds our final hidden state, we generate a uniform time grid of some number of points. We evolve the neural ODE backwards, and we get a whole nicely uniform sample time series of hidden trajectories. And this provides something that's very nice for a lot of these sequence models to be able to interpret without having to worry about all of these gaps or how much correlation there is between points.
This is probably a very naive question. So if your data time series is very sparse, then you will have different trajectories. So in the end, this come up as an uncertainty of the predictions, right?
A little bit. It's probably better to treat it something kind of like a Kalman filter, where we have kind of like a uncertain evolution that gets corrected by the GRU every time we have observations. Though there is work being done by the team who's at Northwestern on trying to model the progression of the hidden states and find out if we can use it to determine uncertainty information in the representations that we get and what other kinds of information we get out, like how they spread in latent distributions and things like that. Yep.
Yeah, so the naive question. So the hidden state, was that a vector? Like, how should I think about
It's a vector. Yep. It's just in this case, for the model that we published, it is 128 numbers as a vector.
And it is giving like the current best guess for how to classify the object, or how should I?
It is giving, so it doesn't necessarily have a directly interpretable meaning because it is a deep hidden layer in a neural network, but essentially something like that. It is a vector that represents all of the information that the neural network is going to need to know at this point to be able to do the downstream task that's currently trained on. Yes.
And you have the network that tries to find the HDT as this vector.
Yes, exactly.
Which
That is a neural network itself, DHT.
right. So could you help me understand why knowing how much future or like why as a function of time, how much information you're going to be needing to use is useful to the neural network?
Okay, so there's been a couple like different attempts to do this. The problem is again, like decorrelation timescales, the further apart your data are, the less likely that they're going to be as impactful, right? If I have like, two data points that are very, very far apart, but like very high in magnitude, that might have different amounts of information in it than two data points that are very, very close together and very high in magnitude. And figuring out how much of that information to weight is going to change based on those time lags, based on other systems that it's observed, which is what's learned. So other attempts have been made to try to do this. Like a classical one is you take the previous hidden state and you just like do e to the minus t times it to do like an exponential decay on it. But these may be not simple or very nonlinear types of relationships, and we want to let the neural network figure it out because we probably do better than anything I can guess.
Great, thank you.
So we have our now nicely uniformly sampled hidden trajectory. And we use another neural network called deep sets to aggregate it all together. It's a little diagram of it, but the way it works is actually fairly simple. We just take each of these hidden trajectories and we run the same residual network, which is just a neural network, special kind of neural network on each single one. We concatenate with the times. And this essentially is kind of like a 1-by-1 convolution. And we just add them all up together into a single vector and run that through another neural network. And now we have a pooling of all of the data from our hidden states that works pretty well at determining what the best representation is. One way you can think of this is almost kind of like a weighted mean in a way, because as the hidden states evolve, they're going to have some information about how much information they have. And the residual networks can extract that, weight them, and then pool them all together to determine what the best representation is for the state. And lastly, when we do this final step, we take our final hidden state and we just do a linear projection to our latent variable. I'm not going to go into this if you're familiar with variational autoencoders. This is just our step of sampling the approximate posterior. If you're not familiar with them, we can talk about them later after the talk. So then we have our small dimensional encoding of our entire light curve, and we want to decode it somehow. which brings us to the SELDON decoder. So here, again, Z is my little latent representation. I've compressed it down now to a small number of, or a smaller dimension than my hidden states. And I'm going to cut it up into 3 little sections. So the first component will be just one number, and I run it through a small MLP. MLP is a multi-layer perceptron, just a neural network. And this will produce a T offset. So part of this is that 2 light curves that are shifted in time shouldn't have significantly different latent representations because they're the same object. So we want to keep this latent representation from having a lot of time variance with it. So by doing this, we can make sure that the rest of these components stay time invariant in some way, that they're much more useful for classification, because if I observe the same light curve, but just time shifted, I shouldn't be saying these are 2 dramatically different things. That's just an observation artifact. The second component is a global amplitude. It's just how big is this light curve? How high is it? And the rest of the components are decoded into a set of basis functions that we'll use a linear combination of to determine what the shape of the light curve is. So we have something that tells us basically, an observational artifact that we can subtract out, how bright it is, and then what is the shape of the light curve. And then for the original SELDON model, we just use Gaussian, so this decodes them as a set of widths, centroids, and amplitudes. But the cool thing about this is it doesn't just make point predictions for next times. It is decoding parameters of a general function. So it doesn't actually produce fluxes directly as an output. It produces a function of time that's filter dependent that you can evaluate at all times, past, present, and future. And again, a more boring diagram of how it works, essentially the same model, but just the summation of all the components. So then we need some data to train this on. So currently we are training on a data set called Elastic, which is a set of simulated light curves made based on Rubin's cadence and observing schedule. And these are designed to kind of simulate what we'll actually have from Rubin in the future. Problem is, Rubin has not been around for long enough to provide us with, 200,000 light curves that we're going to need to actually be able to train this thing. So this is what we have that's good enough for now. Of course, there will be some discrepancies between the simulations and real data because the simulations themselves aren't perfect, but it's the best we can do. Yes?
I thought there was going to be 10 million light curves in it.
Alerts per night.
Alerts.
Not all of those are light curves, and not all of those are, or I guess all of them are light curves because it's at least 1 point, but not all of those are transients that we care about. And we also need enough data to be able to train. If we only have like 1 observation, it's probably not worth inputting to the network for training. And this again is designed to, simulate LSST like cadence, sparsity, things like that, all the challenges that we'd have in the real world. And of course, as with the real world, it comes with different imbalances between all of the different classes. So here, the plastic sample was what Elastic was originally built from, but it has a similar breakdown of the different classes. So to do this, the ratio of different classes in Elastic isn't necessarily going to line up with what we actually see in Rubin. So we try to marginalize that out. We just weight all of our filter bands and different class of transients based inversely proportional to their frequency so that the network's kind of more uniform over the entire set of observations. So we built SELDON and we've trained it a lot and tuned it and all that stuff. So now we're going to evaluate it. So the thing we have to do first, of course, is we have to compare it to other time series modeling architectures. So we took some of the components of SELDON and ran them on their own to see how they do. So we compared this against a pure deep set encoder. So if you remember, the deep set is I just take all my light curve points, I run the same neural network on them, add them together, and then I get my output and run that through my decoder. I run a regular GRU recurrent neural network without the ODE update steps between them, and I run SELDON. On these plots, the closer to 0 that they do, the better. As you can see clearly from these, that SELDON does do the best of the 3 methods. And outperforms all of these in most tasks. This is also a relatively older plot. We've gotten this down quite a lot since then. So these are what the forecasts look like. We just have a pure gated recurrent unit encoder. Again, huge problems with this, mostly because it has no idea how to handle the differences in time lags between observations. It's just too difficult for it. This is also just using a pure deep sets encoder. Big problem with deep sets is when we do the pooling, you can add some kinds of attention to it, but usually just linear attention. And that generally isn't good enough to actually build any of the correlations between data. It only can say there's a set of functions that this might fit, and then maybe try to choose the best one if you want to give it to interpretation to it. And then we run SELDON with ours. So I have a nice little animation of a light curve. So the points get filled in as SELDON sees them, and then you can see SELDON's forecasting prediction. And nice thing about SELDON is once it is trained, it's actually pretty good at forecasting light curves on the fly. And it can quickly achieve like good quality forecasts even before the light curve peaks, which is pretty critical, especially if you want to do spectroscopic follow-up, because spectra take a while to take, and they take less time if you take them when the supernova is at its brightest. And also SELDON's relatively fast on H100 GPU. It can process about 5,000 light curves per second, which is more than enough to process the alert stream from Rubin. And then we wanted to apply this to some real data. So I took some light curves from the young supernova experiment, which only have data in G, R, I, and maybe sometimes Z, and ran SELDON on them. So again, as points get filled in on the light curve, that's when SELDON sees, and the interpolations go out a couple days before. And we can actually model these without any fine tuning right now. But interestingly, especially, is that you can also do reconstructions in filters that it never saw when encoded, because it knows that there has to be some kind of correlation between all of those things. Yes.
You told me earlier that SELDON's not trained on TDEs. So say you give, I mean, you don't know the class beforehand before you put a transient into SELDON. When does that stop it trying to fit it to a supernova light curve and say, no, that's not a supernova?
It doesn't, it will try to fit, it will never give up. I won't give good fits if you like put in something that hasn't been trained on. So part of the idea of how we built SELDON with these basis representations in the decoder is that we think that for some number of transient classes that we trained on, there is a smaller number of functions that can describe them. And then we can train the model to learn what those functions are and then choose what parameters of them work best to model that thing. So if it's something it hasn't seen, it generally will not do as well on it. Yes.
So I'm noticing in your trained model, because everything needs to be Gaussian and everything needs to be correlated, there's lots of not detects
Yes.
on the right side that I guess it's below the detection of.
Yeah.
Okay.
Yeah, they're below detection threshold. We also do tell SELDON when something is flagged as a non-detection by a survey. It does have an embedding flag for that. And it tends to mostly just ignore these kinds of things, though there is a little bit of a bias in some of the elastic data that there is a correlation between the flux of non-detections like far out and then based on where the light curve is going to peak in the future, which a few other people have noticed. Yes.
So what I understood is that you put the information from different bands and that encodes the information as the observation goes. You try to come up with a general form of something that describes the light curve.
Yeah.
Now, as you said that in the Rubin, you wouldn't have the simultaneous information from different bands. And in the case of AGN, will it be like if there is some sort of time delay between the continuum different bands, will it be missing or will it reduce the time delay? Because
so this will depend. We again have only trained SELDON for transients right now. Options for training in the future are definitely something that we are considering for other kinds of phenomenon, but mostly that will require some reformulation of how we do the decoder, because the decoder right now assumes a form of something going up and something going down, and then never changing again.
So it doesn't take into account if there is intrinsic time delay between different bands.
What do you mean? Oh, I mean, it can. It has all that information in there, right? Because it doesn't need to. So when it's fed in, the embeddings are just literally metadata that is tacked onto the light curve, and it learns any correlations between bands from those embeddings. So if there is a time lag, it should be able to model it in the internal representations.
Okay.
Is there some analog of goodness of fit or likelihood that this reports when what it comes out with at the end is not something that it has learned before?
I mean, not in the general framework, in the many little Python scripts and stuff that we use for evaluation for like, you know, testing and things we do. But other than that, I think SELDON's default module only reports an RMSE, a max fractional error, a mean fractional error, and a mean number of standard deviations, and then a max number of standard deviations.
What are the standard deviations based on?
The
Just the
observed
data?
errors. Yeah.
Oh, awesome. Okay.
So
Model space.
no.
Does calculate the photo Z at some point during this process?
Not currently, but I will get to that later in time.
So I have two questions. So here we see that the light curves are sort of like anchoring themselves to the data points as they continue to observe. So I'm curious if does it predict a full model at every time step?
Yes, I'm only drawing this much of it to show like the predictions a few, like I think it's like I don't know, 5 days out or something like that. But so remember, SELDON decodes a function of time that you can then input time into and evaluate whenever.
Okay. And is like, are there kind of tests that check if the uncertainty, like if we imagine a shaded region around the curve, if the uncertainty of that shaded region, if it reduces, if it is correctly big in the future time and small in the observed time?
So yeah, it's a little bit complicated because there's a few different aspects of uncertainty. So there's the uncertainty from like the noise in the data itself, then there's the uncertainty from the internal representations. I will get to later some of the uncertainty quantification that we do, but it is still an active project that's being worked on by Noel and Jizong at Northwestern.
Well, can I ask one last question?
Yeah, absolutely.
So I know that there's an autoencoder, and then you have your translation into the hidden state, and there's all these multiple steps that you kind of take to process the data, and there's probably like some loss associated with each step. So do you keep track of that loss until the very end? Or where do we start?
So there's a couple of aspects of that. Is that one, as long as the hidden states are large enough, if your model is if your optimizer is well tuned, you don't necessarily lose any information as long as you have enough, like big enough space. Because in a sense, every single point that's going into it has like 3 variables, which is like a band of flux error, and the hidden state is 128 dimensions. There's plenty of space for it to maintain that. Additionally, the nice thing about the GRU or the GRU ODE or the ODE4 methods in general is that they act as residual networks themselves. Because I'm not taking my data and producing the next point, I'm taking my data, producing the derivative, and adding it to my previous point. So residual networks are nice because they always have a representation of your original data that keeps going all the way down the network, and you're only modulating it on the side. But at the GRU hidden state updates, there can be some data loss if your gating is too strong, but it's not something that we've necessarily looked into in too much detail just yet. That's a good question. Oh yeah, as I said, we can also make predictions for bands that were never encoded because there's some intrinsic correlation between all of them in these models. Cool thing that we can do is we can examine some of the latent space, as I said before. So here I have these fancy animations. So here is a type 1A light curve being encoded. And again, as points get filled in, more observations. Here is standard deviation of these latent variables. And this is a kind of weird but informative plot that I made to show how all of the components of the latent vector move as more observations come in. So the way that this is plotted is in pairs of components. So I have a Z sub A here, Z sub B here. The blue is Z0 versus Z1, so the first latent component on the x-axis for this is the second component on this axis, and so on and so forth. So, orange is the third latent component plotted against the fourth latent component, just so you can see how they all move together. So first thing to notice is that points pretty rapidly settle. It's almost kind of like some optimizer on its own. As it's seeing more and more data, it's finding better and better fits, and they don't move around as much, which is useful because this does tell us at least some metric of how confident SELDON is at this point of its observations. You can also see the standard deviation of these latent variables drops relatively dramatically. And then the thing that I want you to pay special attention to, if you recall in the decoder, the blue, the Z0 versus Z1, the first component of the latent vector is decoded to a time offset, and the second component is converted to an amplitude. So you can watch it as this fits, it'll reset a second when it gets to right about here. How the shape of the light curve changes with this variable. So it keeps moving in this direction, and the amplitude keeps changing until it settles on the correct amplitude and position of the thing, which tells us that we're not losing that kind of information from the latent space or anything input, and that the model is correctly taking the rest of the components and putting it all just into shape information, which is extremely useful. Yep.
Some of those Z-band observations this is simulated data or real data?
Simulated data.
Right, so the Z-band observations can seem to be wild up to some point.
Yeah.
But
They just have huge error bars on them of like, signal to noise of like 0.1 or something like that.
But it seems like those points don't have any impact on the result at all.
Which is good. We would want that because a non-detection to us is pretty much, it's not necessarily not different than zero, but we can't really say much about it. But there could be some information in there that got labeled non-detection or flag, and we let the neural network determine how much weight to put into it. But they're generally downweighted.
But they're downweighted, but this is simulated data, right?
Yes.
So the network knows that those are high error points, or it just assumes that this is, wait, it went down, then up again, so I'm gonna ignore that.
So we give it a flag to tell us if in the data it was flagged as a non-detection.
Okay.
So the network knows that, and we don't downweight them ourselves. The network decides whether it wants to or not.
But in general, the network does not like to go up, down, and then up again, right?
Yeah, that's also going to be some aspect of it.
Yeah.
Absolutely. It actually can a little bit. It can do maybe like a few bumps. You do get things like, iron 2 recombination features, like in type 1A supernova going up and down for some of the simulated light curves. But don't really trust the elastic models to be all that physically accurate.
Well, so what about things like supernova imposters or the rewind?
So
if they're not in the training set, I guess it doesn't know about.
it does not necessarily know about them. It will try to fit a curve to them. But when I talk later about extensions that we're adding to SELDON, that will become more relevant. This is so far has mostly just been the original SELDON that we published in AAAI last year. And part of this talk will be some of the things that we've been doing with SELDON since then to make it more flexible and more modular to be able to handle a lot more different kinds of tasks.
So this is young SELDON.
Yes. And here we are. So extending SELDON, things that we've been working on since. So first, the original SELDON was actually only trained on type 1A supernova, so that was a pretty big limitation. But since then, we've trained it on all of the transient classes that are inelastic, and it still does fairly well. So here is just like a type 2. This is whatever simulation it came from inelastic. You can see it's still, at this time, providing us pretty good fits. Another fun plot to watch is all the latent vectors, bounce around and eventually settle into their best representations. Next one is doing uncertainty quantification with SELDON. So before, you may have seen some error bars on those plots. Those error bars are mostly based on resampling from the latent distribution. This has a couple problems. One, latent distribution is not properly converged so that everything's Gaussian. They're not all that accurate. And two, you have to resample it. Like those previous plots were made by resampling SELDON 500 times, which, that brings us down to 10 light curves a night that we can process, or a second that we can process. So instead, I added a small neural network extension. All this thing has to do, it makes a Gaussian approximation and takes in our predictions and then stuck on with the original embedding that generated them, which will include intrinsically information like how far away is this point from the starting observation that we had, and then put some nice little 1 sigma error bars on it by just training on, again, Gaussian distribution, normal distribution loss function. And this is another young supernova experiment light curve that's been we applied SELDON to, and you can see that the error estimation is doing pretty well at keeping all the data within its error bars. But also the big thing is that this is just produced now when you run SELDON like automatically and takes, I don't know, like 100 nanoseconds or something versus, running the whole model 500 times in a row. It does make the latent distribution errors a little bit bigger, but that's probably good. It means that we're getting a better idea of how much intrinsic variability there is in our hidden states and latent state approximations. The next extension that we're currently working on is actually a classifier. As I said before, it can produce shapes and functions, but the actual parameters of a series of Gaussian modeling a light curve doesn't actually tell you the class. Otherwise, we have to write something that tries to fit a bunch of actual objects and then make a mapping between those. But that's, at that point, it's not all that useful. So instead, we built a small model for classification. And now this model can actually be generalized to a lot of different purposes, which is kind of nice. This is what's called an energy-based model. And the way it works is it just provides class probabilities by computing the joint distribution of one of these latent representations with a class embedding. So if when training, we know a class, we feed the class into this thing, we feed the latent embedding into this, and it just outputs not a probability, but an energy. And the energy can be turned into this probability, if anyone remembers from the thermodynamics class, the Boltzmann distribution. All you gotta do, e to the energy of the joint probability of these two things, divided by all possible configurations of the system. And there you go, now you have your probability for class. This summation is really easy to do. We have 10 classes that we're training on, add 10 vectors. This integral is completely intractable because taking continuous vector over all space in high dimension, trying to integrate it. But it turns out when training energy-based models, you can sample from this distribution that you have at a current state and generate new samples, and they act as approximations of or at least representative approximations of the distribution that you can use to approximate your partition function. And this works fairly well for doing this. You have to do some special samplers, but luckily autoencoders or modern machine learning codes are all autograd engines, and you can use things like Langevin sampling to sample really, really fast. Additionally, this energy-based model helps a lot with our latent representations. So here is a UMAP projection of the latent vectors for all of our samples, color-coded by a few different supernova classes. You can see there's not good separation. Just by adding this in to training, this doesn't affect the decoder, it doesn't output anything. All it does is help the classification, but it's trained at the same time. The encoder also has to make sure it produces good latent representations that are consistent with class. And it significantly improves the separation between classes in the latent space, which starts to add some interpretability to the model as well, which is also very nice. And then something I've been working on mostly lately is a much more physics-informed decoder. I wasn't all that happy with just having a series of basis functions model thing because it's just like a neural network. But I want something that's a little bit more inspired by the way that we observe things. So in reality, we got LSST, when we're observing something, we put one of these little shiny pieces of glass in front of the camera, and it only lets some light through, and that's how we get an observation in a specific filter band. Each of these filters has a specific transmission function that allows light through at different wavelengths and different amounts. And in reality, there's some sort of spectral energy distribution that describes all of the transients or whatever information that's coming in. So I thought, well, what if SELDON didn't produce just flux estimates, it produced spectra, and then we just pretended to observe the spectra? So it requires a couple more components. So first, we had to add another parameter to be decoded, and this is a redshift, or not necessarily true redshift, is an internal representation redshift. It is a number, and it is treated like a redshift. Making it actually line up with the true redshifts will require a little bit more training, though it does better than I expected. So we take the time and we shift to the rest frame of the observation. And then the decoder has a static grid of wavelengths that we can specify or users can input. And we also redshift this to the rest frame. And then we have a new physically inspired basis. We take this wavelength grid, we run one-by-one convolutions. There's no correlation necessarily ahead of time between wavelengths on the each wavelength coupled with the latent embedding, and this produces something that looks like a spectral energy distribution inside. And we actually produce a linear combination of them. You can produce as many as you want. And then we have another 1-by-1 convolution that acts on each time point, concatenated with the latent embedding. And this will make a series of time-dependent weights of each SED in the basis. And then you can either have a user put in the transmission function of a filter that you have in the observer frame. Or in a special case, if you want, you can try to learn what the transmission function is, just make it an embedding vector and have the neural network learn it. We add these all together and then sum. And what this does is allow us to take light curves that were encoded in one, completely just trained on one survey, and generalize it to decode light curves in any other filter band from any other survey. So we've actually even tried this with Roman. It does pretty well. So here is an example of just a learned embedding of the transmission functions. We do not use these anymore. We just put the actual transmission functions in because we know them. But interestingly, there's no position information ahead of time. These are all random vectors when they're initialized. And the neural network learns at least to separate them based on their wavelength. Not only that, even in the I-band, you'll be able to see soon, there's this little dip right here, which is part of a thing in the elastic data and in Rubin itself, in that there is some sort of atmospheric absorption in the I-band. You can see a little bit just here of the true LSST filters. Additionally, when I just took these and decoded what redshifts it was predicting and plot against the true redshifts, it actually does have some nice correlation. There's no error bars on these redshifts, but it is actually intrinsically learning just from self-consistent physics what a rough estimate of the redshift might be. And again, we applied this to Rubin data. Sorry, I didn't color my things the same because it was a quick thing that I did in a hack like a week and a half ago. But we're able to generalize it to other filter bands. So these are applied to Roman filters as well that we got from a simulated Roman data set.
Do you have training in the training data set? Do you have the Roman filters?
We added some of the Roman filters, yes. So right now, the way it's set up is you can, when training, it's configured that you can either ask it to learn whatever embeddings you want itself, or it has a big lookup table that you can just specify as an option that has filters for currently Rubin, Roman, and Jada University. So you can add more, and you can also add your own just by specifying a .dat file.
And sort of that, can you give like a generic SED in the training that covers a bigger wavelength range, and then it can calculate?
Yes, so when we train it, we generate, at least in the mode I do, that's why this has come off. I generate the SED over from like 3,000 to like 30,000 angstroms. But that's also something that can be specified during training. Ideally, we would like to train it as over a broad wavelength range as possible. There'll be limits in how you train it, right? Like if I only train with the LSST filters, I'm only going to be able to like really get out to, you know, a factor of a few more than in wavelength, because there's only so much the highest redshift objects that can be in that data set. So the object has to be able to redshift its SED out beyond the filters to actually get some good information. I will say right now, the internal representations of the SED are not as interpretable. They have lines and things that move between filters, but I wouldn't say they're quite physical yet. But that is something for the future. So the things that we want to add to SELDON in the future is multimodality. There's lots of different kinds of data that we would like to include, especially in the encoder. We've made the decoder a little bit more flexible, but the encoding is still kind of limited in not understanding all of these different things and how they correlate together. It just builds kind of a big correlation table between everything. So we want to encode spectra into SELDON, which right now we can, in theory, train on spectra. We wouldn't be able to encode them currently with the current architecture, but we can always take a spectrum of an object taken a certain time, and then the internal SED representations, we just do a loss on that, and then that would help at least improve the representations that we're getting. But we would actually like to physically encode the spectra as well, which we should be able to do because spectra are just like more fine-grained photometric data. They're all taken at once, right? Photometry is low-resolution spectroscopy. We would like some host galaxy information, both from metadata, either like fits to parameters of the host galaxy or things like the host galaxy flux and different filter bands. And especially we would like to train on the whole image of the host galaxy as a modality for SELDON, because that has a lot of information about, what kind of object it is based on where it is in the galaxy and what kind of galaxy it's in. And then lastly, we would like to eventually align SELDON with simulated models, well, specifically emulation models, because simulations are too slow. We would like to have latent representations that can be mapped to autoencodings in other emulators so that we can take SELDON, generate encoding of a light curve or any transient that we see, map that onto an emulator, and then kick out what parameters of the simulation generated that object, all to do at once. And of course, SELDON, as I mentioned before, as a transient foundation model, it's still in early phases, but ideally it will be part of a much larger framework. We would like to do eventually real-time classification, especially both spectroscopic and photometric classification, which will also incorporate other models that we're working with in our group, such as DASH. And we'd like to do multimodal learning to have kind of one general big foundation model. And now, again, SELDON is mostly the encoder with a few modular components on it that helps it train, but we would like this to all come into one larger framework in the future. And we would like to deploy this, of course, as a real-time broker for LSST alerts to not only be able to provide classifications or forecasts, physical parameter inference or things like that, but also for the purpose of active learning, we would like to keep adding data to our training set as we get it in, and we plan to deploy it onto Open Science Grid, which we're working on currently, so that is set up to continually train periodically whenever enough data has come in from Rubin to add something that's worthwhile for running it. Thank you all for listening to my talk. Happy to take any other questions that you have, and you can find the paper here. Have it up on archive. I think it's on the proceedings now for AAAI, but sometimes they're a little slow with that.
Any more questions? I have other questions about this last one. So when it comes to using these line curves to try to look at standard candles again, how much error comes out of this? How have you done that sort of analysis to see how the light curves stack up on the type 1A supernova?
We have not actually tried applying it to cosmology yet. That's something that we'll probably be doing once we release this next version of SELDON with all these upgrades. That's definitely an interesting thing to try out, especially for like light curves that are very, very sparsely sampled. See if we can improve distance estimates with it.
Any other questions?
Follow up on that. What's your lower limit of the number of points before you start tomorrow?
So in training right now it is 11. And that was chosen mostly so that we try to have a couple of observations in a couple of bands at a time. And we also augment the data heavily. We'll drop out whole bands or even just train on like a single band randomly. We'll randomly make the data even more sparse. We'll cut off the data in different sliding windows, all kinds of things. But we're still investigating how number of points affects the quality of the predictions, because it's not just a matter of number of points, and it's not just a matter of time lag, and it's not just a matter of net signal noise. It is some complex combination of all of these, which again is an active thing we're working on.
What are prospects for using this tool for multi-wavelength SED modeling for things like galaxies and other stuff? I know that's not time variant, but like, do you think that this will incorporate that information to inform its like transient modeling or? So
for now, if we do incorporate that, it will definitely be metadata because it's not time series data. It would be used for improving transient modeling. But other than that, we wouldn't be able to like model galaxies themselves, at least with the current representations we have, because it's not, transient. But I have thought a little bit about, instead of just decoding an SED, I decode a data cube that's an image of SEDs and then applying aperture to it and then integrate. In that case, I would also do a data cube of the galaxy image and then subtract it off to make sure that we're doing the whole pipeline.
Can I ask a follow-up question? So thinking about type 1A supernova modeling, do you expect a sort of joint model of the host galaxy and the supernovae that will, from using this data cube?
So
You're building.
maybe not the host galaxy directly. I think if I had too many features, got them, or Noel will kill me. But I think that we will definitely. So I think the way that SELDON is eventually going to work out is once we include these kinds of extra metadata into the encoding, we will essentially use SELDON as an embedder for a larger framework of models. So we can do things like joint embedding between SELDON and like AON to try to build like a more information-rich latent representation of different sources that we see. And that's probably the way to go in the future. This is especially the way that a lot of these like big models work now. They're not like really one model that does everything. It is a series of different joint embedding encoders that all specify or specialize in a specific modality and then it's aggregated together to do some other downstream tasks.
If no further questions, I will ask one.
Yep.
Real quick. I heard two constraints on inside of the model that weren't necessary for the neural network. One was that in the end you're assuming something Gaussian. And then the other was that it couldn't go up, down, and then up again.
Mm-hmm.
So is it just one sort of skewed Gaussian or something like that that you're using?
So right now it just learns parameters of basis of Gaussians. So it can go up and down a number of times equal to the number of Gaussians you choose in your basis.
Right.
Which when we trained it was 8, I think. But the idea of this is to be able to handle little bits of variability throughout the thing. With the spectral basis decoder, those constraints are now gone entirely. It just generates linear combinations of what it thinks the SED might look like over time and then weights them. And it still actually produces things that are actually better matches to like curves than we had before.
So in my sort of naive perspective, I noticed the shape of the curve does look like a skewed Gaussian, and I noticed that you have. So my question is, if you put one more parameter out for the Gaussian, the skewness of it, does that help the training at all?
So we actually did test this. So we tried a few different things. So we tried linear combinations of sigmoids, logistic functions, pairs of sigmoids, which is just logistic function. We tried Gumbel distributions, and we tried a few models from different papers in the literature of people building parametric models of actual like supernova. And the problem is that the more we try to restrict those, the harder it is to like expand to other modalities. But skewed Gaussians aren't too bad. But the thing that I want to move away from is making some general basis assumption. I'd like there to be like a little bit more physical motivation for why the light curves look the way they do.
Okay. All right. Thank you very much. All right, let's thank the speaker again. Please come join us next week. Susan Benson will be joining us. And we have the schedule full for the rest of the semester, so please continue.